Every minute an assembly line sits idle, global manufacturers lose thousands of dollars. When a critical CNC machine fails, the clock starts ticking instantly. The technician scrambles to find a fix, digging through a massive, unstructured 600-page digital manual to identify the problem and get the machine back online. Here is where the system breaks. The technician types "broken drive motor" into the search bar, but the engineering manual classifies the issue as an actuator E409 fault. The result is 0 matches. This happens because traditional search engines operate strictly on syntax. They look for flat, one-dimensional, exact character matches. If you don't type the precise string of letters, the information remains invisible. Today, enterprises generate mountains of unstructured data. Millions of technical manuals, complex sensor logs, intricate wiring schematics, and diagnostic images. Applying a linear, exact match tool to this level of complexity is an architectural mismatch. It treats a highly technical library of engineering data like a simple spelling test. When a system only indexes spelling, it completely fails to understand human intent, context, or actual meaning. To solve this, we use a vector database. Instead of storing text as a flat sequence of words, a vector database converts unstructured documents into mathematical coordinates. This process relies on embeddings. An artificial intelligence model reads a paragraph of text, a data table, or even an image, and translates it into a dense vector, a long array of floating point numbers representing its semantic features. You can think of these long arrays of numbers as literal coordinates in a geometric space. In this space, concepts are organized by their meaning. A point representing the word dog will plot closely to a point representing puppy. Meanwhile, a point representing car will plot far away in a completely different quadrant. Modern embedding models take this physical mapping and expand it to thousands of dimensions, allowing them to plot incredibly nuanced, enterprise-level relationships across vast datasets. In this high-dimensional space, the plain English phrase "broken motor" and the highly technical schematic for an E409 fault are plotted in the exact same mathematical neighborhood. With this spatial mapping, finding information is no longer about scanning a document page by page. When a user asks a natural language question, that question is instantly converted into its own vector and dropped directly into this multidimensional cloud of enterprise data. The system then uses nearest neighbor search algorithms. It draws a radius around the query and identifies the specific cluster of data points located closest to it. By calculating the literal geometric distance between the query and the data, the algorithm completely bypasses the need for exact word matches. Powered by highly optimized indexing tools like Google's scan algorithm, this geometric retrieval executes in milliseconds, even when searching across billions of data points. We have upgraded search by teaching computers how to measure the physical, mathematical distance between concepts. Let's return to the factory floor breakdown. This time, we equip the engineer with an AI copilot connected to this vector architecture. The engineer doesn't need to guess keywords. They simply speak into their device, asking how to clear the specific E409 error code using natural language. To maximize accuracy, the system uses hybrid search. It merges the exact keyword precision of traditional search for specific serial numbers with the broad semantic understanding of dense vectors. This perfectly retrieved data now flows into the final architectural step, the Retrieval-Augmented Generation, or RAG pipeline. The RAG pipeline takes the highly relevant manuals, tables, and wiring schematics retrieved from the vector database and feeds them directly to a large language model as context. The model synthesizes a step-by-step procedure based on the retrieved documentation, providing the technician with the specific torque values and wiring sequences required to get the line back online. In this architecture, vector databases act as a factual long-term memory. By grounding every response in these retrieved snippets, we significantly reduce the risk of the model inventing its own technical facts or ignoring the reality of the engineering manuals. Mapping the space of meaning bridges the gap between how we record technical data and how we actually use it. It turns a static library into a functional map, where the distance between a question and its answer is finally something we can measure.